For everyone who's joined, we're just waiting for Dr. Bhattacharya to join the session. Until then, I would just like to mention that we have power one-on-one mentoring sessions with industry experts, and you can connect with them and seek guidance for 15 minutes one-on-one sessions in the lounge area. I think we have Dr. Bhattacharya with us. Dr. Bhattacharya, can you hear me?
Hi, yes, I can hear you. Can you hear me?
Yes, I can. Will you be switching on the camera because I can't see you?
Okay, yeah, let me switch on the camera.
Yeah. Yes, I can see you now.
Okay.
Okay. Hello, sir.
Hi, it's good afternoon.
Good afternoon, sir. Yes. So welcome back, everyone, and welcome, Dr. Bhattacharya. To everyone attending, I'm just going to quickly introduce your profile and about the talk, and then we can start with the session. Is that okay, Dr. Bhattacharya?
Sure.
Sure.
Thank
Yeah.
you.
Okay. So yeah. So our next speaker is Dr. Sourangshu Bhattacharya, professor at IIT Kharagpur. Dr. Bhattacharya holds a PhD in computer science from IISc Bangalore, and MTech in computer science from ISI Kolkata, and a BTech from IIT Roorkee. Before joining IIT Kharagpur, he was a scientist at Yahoo Labs, Bangalore, and a visiting scholar at the Helsinki University of Technology. He has more than 20 publications in top international conferences and journals. Today, Dr. Bhattacharya will be talking with us on AI applications in autonomous driving, where he will be discussing the problem of data efficient training of autonomous driving systems. The talk will be followed by a Q&A session. So attendees, please feel free to drop your questions in the chat box or the Q&A tab. So without any further ado, we'll start. The screen is all yours, Dr. Bhattacharya.
Okay, so I'm trying to share my slides. Are they visible?
Yeah, it's visible and they're in full screen as well. Thank you so much.
Okay. Thank you very much. Okay, so thank you, Kashyap, for the introduction, and thank you for giving me this opportunity to talk to the audience here in this conference. So today's topic is going to be scalable AI for autonomous driving. Okay, so okay, yeah. Okay, so so actually there is a lot of things on the screen. I don't know how to. So uh, let me try to remove some of the things from the screen.
We can only see your presentation in full screen mode,
Oh,
Doctor.
okay. You can see our presentation. Okay, because I'm seeing some other things. Okay, so good. If there is no obstruction, let me go ahead and yeah. Okay. So, but yeah, it's yeah. Okay. So so this is joint work. So today what I'm going to describe here. So it's based, basically on two of our recent works. Okay, one is it has been published in patent recognition letters in 2020. It's called multi-criteria online frame subset selection for autonomous vehicle videos. And the other one is on archive. It's called convex online video frame subset selection using multi-criteria for data efficient autonomous drive. Okay, and this is joint work with my PhD student Shomi Das. Okay, uh, Suparna Bhattacharya, who is my collaborator from HP, Okay, Professor Niloy Ganguly, who is a faculty member at IIT Kharagpur, and myself, and some more students whose names are appearing on the screen. They are all student. They were all students at IIT Kharagpur. Okay, and this is kind of a joint collaborative project between IIT Kharagpur and HPE. Okay. Uh, so this is the outline of my talk. So I'm going to briefly talk about autonomous driving and how we do experiments or how we do development of software for autonomous driving. Okay, and we are going to discuss a simulation platform, which is the CARLA platform. Okay, then I'm going to give some overview of what are the state-of-the-art methods for different AI problems which are needed to be solved for autonomous driving. Okay, and then I'm going to briefly motivate the need for scalability uh, in autonomous driving. That is to say that the AI applications that we use in autonomous driving, uh, they need uh, uh, they need to be scalable with respect to the volume of data that we collect. Okay, and then we are going to discuss mostly one of the published methods, which is multi-criteria online subset selection. Okay, and there is an improved version of it, which is called the thresholded multi-criteria online subset selection. Uh, and we are going to, tell you some results on this. Okay, so okay, so. So the first thing is that in order to work on online, on autonomous driving. Okay, there are of course many ways. So some of the companies, they have access to vehicles which actually have all the sensors and cameras and stuff, and they collect data, and then they also so they develop their autonomous driving systems, and then they deploy these autonomous driving systems onto the vehicles, and then they go ahead and test in the real world. Of course, this requires a lot of resources. You need a lot of funds to get the experimental setup, and then also you need a lot of engineering, to actually fit the sensors, all the sensors into the vehicles, get the data, do the processing, and then go back and deploy the trained AI models, and then test in the real life. And also, it is somewhat hazardous in the sense that if you deploy it in the real life, and if your model is not that good, then what may happen is you may encounter an accident or something like that. Okay. So another approach that can be taken, which we have taken in our case, is using what are called driving simulators. Okay, and CARLA is one of the open source driving simulators which we use. So, what is CARLA? So, it's basically a piece of software. It's a piece of open source software. It's developed by folks at Intel. Okay, and it supports development and training and validation of urban autonomous driving systems. Okay. Uh, so it provides you the maps and the layouts of buildings. Okay. Uh, so it has two maps. Then it has various weather modes. Okay. Uh, and then it has support for having dynamic objects on the map. Okay, the dynamic objects can be other vehicles, they can be pedestrians, etc. Okay, so these are the two types of dynamic objects that you can have. Okay, and what basically the software platform will do is that, given the position of your vehicle, it will generate various sensor outputs. Okay, so So some of the sensor output, so the most obvious sensor output is a camera, which is what we also use, which is that, it will generate an image which will reflect as though you are standing in a city in a particular position with a vehicle, okay? And you are viewing it from a camera, and you can use different camera angles. There can be forward camera or a sideways camera, etc. Okay. You can also ask for other sensors. For example, you can ask for a depth map. So here on screen, I'm showing the camera here, okay, and this is the depth map. Okay, the black and white picture is the depth map. And another kind of sensor which you can again take is something like semantic segmentation sensor. Okay, so where it basically shows on the image itself the type of object that is represented at a particular pixel. Okay. Moreover, of course, the CARLA simulator also has a map. So here on screen, I'm showing the map of a particular town in CARLA. Now, these maps have what are called waypoints. So the red dots that you can see here are the waypoints. Okay, so these are the points from using which you can basically define the poses or the episodes. Okay, so basically you start from a origin waypoint and you pass through certain waypoints to go to a destination. Okay. So this is all provided, okay, and of course it also provides a module, a route planning module, where if you give an episode like this, which is a set of waypoints, okay, then it will basically be able to generate the driving directions at a given point in time, whether you have to go straight, you have to go left, you have to go right, and so on and so forth. Okay. uh, so these are some of the facilities that CARLA provides. Of course, there are other simulators also available uh, for the same purpose, but they are not as advanced as CARLA. So I have just named some of them for completeness sake, but CARLA is kind of the more comprehensive uh, for development of autonomous driving system in the urban environments. Okay. And so I'm not sure if you can see. So I'm just showing a video that we generated when we ran our system on CARLA. Okay, so when you do a CARLA setup, and then CARLA also provides its own driving model, which is based on the ground truth. Okay, so it knows where to go, so it knows exactly how much you have to go in a particular direction. Okay, so here is a driving video that you can see on the screen. So basically you are seeing, so all this data is being supplied by the CARLA simulator. Okay, so on the left here you can see image from a left camera. Center is the straight camera image. So for our experiments, we use mostly the straight camera image. And on the right here, you have the right camera image. Okay. And on the bottom left here, you have the vehicle's actual position on the map in real time. Okay. And on the bottom right here, you can see various affordances, which are also being, which are basically, certain attributes that we calculate for the driving. Okay, like something like red signal, speed sign, etc., which are also, which are also being provided by the CARLA. Okay, so let us go ahead. Uh, Now, what are the AI problems that one tries to solve for autonomous driving? Okay, so there are many different AI problems that one tries to solve for autonomous driving. Okay, the first one you can see here on the left is the semantic segmentation problem. So, what is the semantic segmentation problem? So, you are given an image or a picture like this, and you want to find out a segmentation of the image which shows for each pixel what is the corresponding object. Okay. Another AI application which is very common or very which is an important or integral part of any autonomous driving system is the driving model. Okay, so the driving model, again, it takes image as input. It may take some auxiliary information also as input, including some driving directions, etc. And then it tries to predict, let's say, what is the steering angle, what is the throttle, uh, what is the brake, etc. Okay, so we have worked on mainly these two types of models. Okay, but of course there are many other components that is required for autonomous driving to work, including, for example, various object detection components like traffic sign detection, pedestrian detection, vehicle detection, etc. Okay. So what is semantic segmentation? So as I described already, it basically takes an RGB image or a grayscale image, as the case may be. We mostly work with RGB images today, and then it produces uh, output segmentation map, okay, which is of same size. So if the input size is H times W, then the output size is also of H times W. But now it has got C channels, where C is the number of semantic classes. Okay, so depending on the depending on the scenario, you may have 10 or 20 driving classes. So for example, some of the classes can be road, sidewalk. So in case of uh, in case of autonomous driving, you can have vehicles, pedestrians, road, sidewalk, building, uh, traffic posts, etc. Okay. Uh, okay. And basically, one of the there have been a lot of research in the computer vision community on designing models for semantic segmentation. So one of the best performing models is a model by Google called DeepLab V3 Plus. Okay, and this basically uses the concept of actress convolution layers, and there are many improvements which have been done over these actress over this thing. But one of the main ideas that they propose is the actress convolution, which is the convolution with convolutional neural networks with holes in them. Okay, and that has kind of resulted in a lot of improvement. And in the bottom, you can see that they are kind of the best performing in many of the categories. Okay, not just autonomous driving. Okay. The other important component is the autonomous driving model. So how does the autonomous driving model work? So here in the left, you can see a simulator agent, okay? And below that, you can see the route planning module. So basically the simulator agent provides data to the perception module. Okay, so the perception module is the module of the autonomous driving system, which takes in the information from the surroundings. In our case, we have only taken camera input, but some of the other autonomous driving systems, they also take, for example, lidar data from lidar, and sometimes radar also. Okay, so whatever sensors are available, they can be used as an used for perception of the environment, and those basically become the perception input. Okay, and the route planning module basically gives you the directional command, which is to the intended direction where you want to go. Okay, so whether you want to go straight, left, right, etc. Okay, and now this whole information is fed into a neural network model. Okay, and your neural network model produces finally the output, which is steer, throttle, and brake. So these are the basically the three types of output. So steer is the steering angle of the car, throttle is the accelerator, and brake is of course the brake. Okay. So I will come to the affordances in a minute. Okay. Now, what are the different driving models people have been working on? So people have been working on driving models for a long time. Okay. So some of the oldest driving models were came out of the DARPA Grand Challenge, like something like there was the Stanley model by Stanford, and there was the Bartha driving model by Mercedes, and these are just some of the samples. These are all called modular pipelines. So the key idea here is that they had very specific engineered models for different perception tasks, okay, and different perception models, and then they had sort of a controller, which is the neural network controller, okay. So later, in 2016, 2017, there was a system called PilotNet, which was sort of demonstrated by NVIDIA, okay, where they said that one need not have such a modular approach from the AI point of view, okay, or from the deep learning point of view, but you can have an end-to-end learning approach where you directly give the sensor inputs into a very deep neural network, and you can get the output. And this sort of started the research. I mean, this prompted more and more research and models for towards the autonomous driving. Okay. So what are the different paradigms? So two of the most leading paradigms today are, one is using the conditional imitation learning, which many people have been developing, including those from University of Barcelona, and also some people from Intel and some people from California. Okay, where they are basically so the key idea here is that the model is a deep neural network model. Okay, it learns by imitating an expert. Okay, and but the learning is conditional on the driving direction. So the basically the learning model takes as input the driving directions, and the neural network learns by imitating an expert driver. And there are various things reported which basically provide improvement in handling bias and overfitting issues in real world scenarios. Okay. The second approach which we follow is the affordance learning approach, where instead of, so this is also an end-to-end learning approach. However, instead of trying to directly predict the steer or throttle, what we do is we predict the affordances, which are simple explainable quantities which govern the driving decisions. And then those explainable quantities are passed through certain rule-based systems, okay, to actually come up with the controller, okay, come up with the driving decisions like steer, throttle, etc. Okay, so what are the affordances? So we follow this work of conditional affordance learning, which was published in 2018. Okay, uh, and they basically used the three discrete affordances and three continuous affordances. So the discrete affordances is the situation a hazard stop situation, that is currently is there, for example, vehicle directly in front of you or a pedestrian directly in front of you. Okay. Then red traffic light situation. Okay. So basically the situation says red traffic light, so you have to stop. Okay. Or something like a speed sign situation. Okay. Which is that, there's a speed sign which is asking you to slow down, etc. Okay. So these are the three discrete affordances. Okay. And the more important affordances are the continuous affordances. So one is that you predict the distance to the vehicle in front. Okay. Then you predict the relative angle. So the angle your vehicle should make relative to the center line of the current road. Okay. And distance to center line. Okay. So if you have a current lane, okay, uh, what should be your distance to the center line of the current lane? Okay. So these are the things you predict. Okay. Um, okay. So and you can calculate these things from the CARLA simulator. So we will skip this detail in the interest of time. And also we can use this conditional affordance learning model to finally get the steering, throttle, etc. Okay. uh, we will skip these details. Okay. So now we will come to the need for scalability in autonomous driving, which is our one. Okay. So as this slide tells you, all the companies that are going into autonomous driving, or anybody who wants to develop an autonomous driving system, collects billions of miles of data and petabytes of data basically. So some estimates say that Google self-driving cars collect 750 megabytes of data per second. Okay. So here is the back of the palm calculation, which shows you that basically you collect something like per hour 1 terabyte of data. Okay. And basically you, of course, you don't store all this data, so you have some data compression using MPEG, etc. So that gives you a compression ratio of about 70:1. Okay. And now, if let's say we are trying to do edge to core transfer, uh, uh, to a data center or something. Okay. Uh, then, and suppose you have a transfer rate of let's say 10 Mbps. Okay. Still, we can do the calculation and check that you need something like a 39:1 compression to achieve this. Okay. So this is just one case I am making for the situation where you really need to compress the data that is arriving. Okay. And we did some experiments with the conditional affordance learning model. Okay. And we are reporting here the accuracies of predicting the affordances. Okay. For continuous affordance, we are reporting the accuracy, and for discrete affordance, we are reporting the mean absolute. For discrete affordances, we are reporting the accuracy, and for continuous affordances, we are reporting the mean absolute error. Okay. And we are reporting it for two sets of data. One is, we are sampling at about, let's say, 20 frames per second. And other is we are just taking the keyframes provided by the MPEG compression. Okay. So there is a compression here of about 5:1. Okay. So we select only one out of every 5 frames here. Okay. So we are already compressing by 5. Okay. So this already gives and you can see that there is not much difference between the accuracies of these. Okay. But remember, accuracy is not the last word. We have to actually design a system and run it on and train the model using it. Okay. So here we come to this multi-criteria online subset selection. Okay, so this is the system architecture that we envision, which I have already discussed. So let me just skip this. So basic idea is that as the cars are collecting data, and there is an autonomous driving system running in the car. Okay, the autonomous driving system should select the important video frames. Okay, and then the important video frames can be either stored in the car and then transferred through cloud, or it can be transferred to through cloud immediately, as the case may be. Okay. Okay, and the framework basically here is that you have a cumulative set and you have a reduced set. Okay, and you continuously keep receiving these video frames. Okay, and your cumulative set will keep on growing. Okay, but your reduced set is only accumulating data from the selected subset of the current data set. So xt is the current data set, and XSBT is the selected subset of the current data set. Okay, and this is kind of a technical slide. Okay, so what this is basically showing you is it is showing you a convex optimization formulation for uh, achieving this online subset selection. Okay, uh, and here the main idea is that there can be multiple different criteria for doing this online subset selection. In particular, there can be the pairwise criteria, which measures the distance between different frames. So frame I and frame J, which I am denoting here by Dij. Okay, and there can be the point-wise criteria. Okay, so it can be, for example, how much loss am I incurring, or how much error am I making on a particular instance video frame. Okay, for let's say doing semantic segmentation or prediction of affordances, etc. Okay, so and then here we have a selection variable Zij, which implies that frame J is selected instead of frame I. So frame I can be dropped and instead frame J can be kept. Okay, and basically this says that a joint criteria for of the pairwise and the pointwise criteria can be selected. Okay, and in our works we try out different pointwise and pairwise criteria. Okay, which are state of the, some of them are from state of the art papers. Okay, uh, and we see that as we combine these multiple criterias into optimality, into selection of frames, and then we test on semantic segmentation. Okay, so for example, if we try a 100:4 compression, so this is something like a 25:1. Okay, we get a drop of about 3% in mean IOU score. Okay, which is the most relevant metric in case of semantic segmentation. Okay, if we select using a compression ratio of 100:15, we get a drop of only 2%. Okay, uh, so uh, so we are achieving very high compressions here, almost close to what we want. Okay, not quite as much. We want something like 40:1 compression, uh, but we are achieving close to with minimal drop in performance. Okay. Uh, okay. So now I'm not going into the key idea of this thresholded multi-criteria of online subset selection, which is similar to MCOS algorithm that I just defined, but it avoids sort of a double counting problem, which is there in that problem. So for reference, I would request you to read our paper, the reference for which we have already given. Okay, but I would like to highlight some of the results that we got using this. So you can see that this is the episode completion. So basically, one of the ways of saying how good, or rather the best way of measuring how good a driving model is to see what fraction of episodes the car is able to complete without getting into an accident, or without basically without making an error. Okay. And you see some of the so we are able to complete almost all of the 10 episodes, okay, which is provided by CARLA, okay, using using this TM cost, and then BL stands for bucket wise loss, okay, this model, okay, and this is for 1 is to 5 compression, which is 100 is to 20 compression, and for 100 is to 7 compression, we are able to we are able to mostly complete all of them. We are just dropping some of the turn episodes, so one turn episode each, okay, one for the turn without the dynamic things like pedestrian, etc., and one turn where uh, there is dynamic objects like pedestrians, okay. So this is much better than some of the other subset selection models, okay. Okay. And the reason, so we analyze in detail the reason, and what we are showing here is that what fraction of frames are we selecting from the left turn situations and the right turn situations. Okay, and we see that we are selecting kind of this blue thing is selecting the highest fraction of frames among all the methods from the left turn and the right turn situations, and it is selecting the lowest fraction of frames, okay, from the straight road situation. Okay, so here is our a video of our trained model driving through a right turn with with the frame subset selected. Yeah, so you can see that it is going really fast on the straight stages, which are easy, and then it slows down at the turns where it is processing much more frames, okay, and then it takes the turn correctly, okay. Similarly, here is this is supposed to be a left turn scenario, I think, or okay, this is a duplication of the thing. Yeah, this is the left turn scenario. Okay, so again, you can see that at the turn, it is slowing down and processing much more frames compared to at the straights. Okay. Okay. And so thank you very much for your attention. And
yes, thank you so much, Dr. Bhattacharya, for your very insightful session. We are actually out of time, so I request people who want to ask questions to Dr. Bhattacharya to ask them in the lounge area. If that's okay.
yeah, sure.
Yeah, sure.
So
Okay. So thanks again.
thank you very much. Thank you very much for your attention.
Yes, thank